Good evening, gents. Good to be chatting to you guys again after such a long break. I hope you guys are managing during lockdown. As I said, I'd make a video of chemical equilibrium. Please bear with me. This is all new to me as well, so I hope it goes well and this is beneficial to you as well. Right, let's get started. Chemical equilibrium. First of all, we just need to look back to rates of reaction. That was a sort of a build-up to chemical equilibrium, and these are just the factors that affect the rate of chemical reaction. Temperature, amounts of moles of reactive substance present, surface area, catalyst. Alright, if those are involved, then it can create that activated complex, and then obviously you need that effective collisions, right amount of energy, and then that forms a product. Right, moving on to matters that are also quite important with regards to chemical equilibrium. We also dealt with exothermic and endothermic reactions when we did rates of reaction. And just a quick recap on that. Obviously, exothermic reactions can be identified when we have a look at delta H here. It's less than 0. In other words, it gives you a negative value, negative amount of energy. And the energy is always added on the product side. Here's an example of that. They give you the chemical equation. They give you this information here as well. That's very important to us. Sometimes they just say less than 0, sometimes they give it to you as a negative value. An endothermic reaction is just the opposite. The delta H is greater than 0, it's a positive value, and that is because energy is absorbed on the reactant side. Okay, and here's just another example of that positive value. This is obviously going to be very important as we move into this next section. Another thing that's also important is identifying the phases. So when we look at chemical equations, there's a whole lot of information available to us that is important and that we need to take note of. And one of those things is the phases. So this is an example of a homogeneous reaction, and it's called that because all molecules involved have the same phase. They're all gases. The subscript over here gives us that information. Same with this one over here. All gases, so it's homogeneous. This one, they don't all have the same phase, so it is heterogeneous. This one is a solid, shown by that subscript S, and the rest are gases. Here, quite important that you identify the subscripts. The only one that we haven't looked at is L for liquid. That's a pure liquid. Another one that we'll also be dealing with is aqueous solutions, which has obviously got the subscript AQ. Alright, so we need to get onto this whole chemical equilibrium thing, and we'll do that by looking at an example over here. Nitrogen gas with hydrogen gas reacting. So these are our reactants, and they produce ammonia, the product. But something that's very important here is the double arrow, which we don't necessarily often see, but in chemical equilibrium it is very much part of the section here. And basically what this tells us is that the reaction can go both ways. It can go from hydrogen to ammonia, or ammonia can break down and form nitrogen and hydrogen again. Obviously in specific circumstances, and that being in a closed, it has to be in a closed container. So some other information here, subscripts for all gases, and this tells us what type of reaction is this. It's delta H less than 0, that's exothermic. So there's an equilibrium that will arise when we have reactions taking place in a closed container, and it is dynamic. It is a dynamic equilibrium. And what this basically means is that the rate of the forward reaction is equal to the rate of the reverse reaction. Okay, equilibrium doesn't mean the reaction has stopped. It's still ongoing. It is just that the rate at which product is formed and the rate at which the product forms reactants again is the same. So there are two terms here that I've now mentioned that might be new to you: forward and reverse reactions. Forward reaction, quite simply, is going from left, from reactant, to right, the product. That's your forward reaction, because we read from left to right. Then the reverse reaction is from product back to reactant, so from right to left. Okay. So, like I said already, at this point for equilibrium, the rate of the reaction which produces ammonia, in this case, equals the rate at which the ammonia breaks down to form nitrogen and hydrogen. So this is a concept that happens in industry all the time, and that's why this is a very applicable section. Okay, I've already mentioned that. Another thing that we need to take note of in equilibrium is the concentration of the molecules involved. The concentrations of these substances remain constant at equilibrium. It doesn't mean that they are the same, so the concentration of the product isn't necessarily the same as the concentration of the reactants. It just means that they are no longer changing. They are the same. Okay. So let us now have a look at a very important principle called Le Chatelier's principle. Le Chatelier's principle states that when the equilibrium in a closed system is disturbed, the system will reinstate a new equilibrium by favoring the reaction that will oppose the disturbance. So when you read this the first time, it would obviously not make as much sense to you, but that's why I'm here. That's why we're going to explain what's going on here. And there are different ways in which the equilibrium can be disturbed, and we will also look at those. Like I said before, the closed system has to be in place for this principle to be applied. And like I've already mentioned, I've already talked about the forward and the reverse reactions. I think that's pretty clear. So what are the factors that disturb the equilibrium? So once things have come to a dynamic equilibrium, what can disturb that equilibrium so that a new equilibrium has to be established? So these are the factors, and they aren't necessarily the same as the factors affecting the rate of reaction. These are the factors affecting the equilibrium. They are different. So the change of temperature, it's a very important one. This is where endothermic and exothermic reactions are so important to identify. So change of temperature is the first one. The second one is the concentration of reactants, or the concentration of the product, and then pressure. This is only applicable for substances that are gases. So the things that don't affect chemical equilibrium are catalyst and the surface area of your reactants. Right, so catalysts, obviously, they speed up the rate of a reaction, but both ways. So they speed up the forward and the reverse reaction at equal rates. So it has no effect on the equilibrium. So let's have a look at how these factors affect equilibrium. So the first thing we'll have a look at is a change in temperature. Alright, so a reaction in which the reaction is exothermic doesn't want to be heated. So an exothermic reaction will be favored if it is cool. A reaction which is endothermic wants to be heated. Alright, so remember, with exothermic reactions, whenever we look at them, I think there was one here, the energy is given off. Alright, this is an exothermic reaction. The forward reaction is exothermic. So energy is given off. So it means it doesn't like heat. It doesn't want heat. So the disturbance here is an increase in temperature. So it's not going to favor exothermic, because exothermic doesn't like heat. So it will favor the endothermic reaction. Because remember, endothermic reactions absorb heat. So endothermic reactions like heat. So an increase in temperature will favor the direction of the endothermic reaction. So let me just clarify here. If we are told that this reaction is exothermic by looking at this information, then that applies to the forward reaction from left to right. So the forward reaction in this case is exothermic. That means the reverse reaction has to be endothermic. So if in this closed system over here we increase the temperature, that's the factor that is changing, and that's affecting the equilibrium. If we increase the temperature here, it's going to favor the endothermic reaction. In other words, it's going to favor the reverse reaction, which means it's going to produce more nitrogen and hydrogen gas. The inverse is also true. So if we had to decrease the temperature here, that means it will favor the exothermic reaction. So that will favor the forward reaction and produce more ammonia. So it's so vitally important for us to know what type of reaction we've got. Is it endothermic or is it exothermic? Because if we know that, we will know what type of an effect the change in temperature will have and which side it will favor, which reaction it will favor, forward or reverse. Okay. Then let's have a look here. One of the factors that needs to be remembered from gas is that when the pressure of a gas is increased, so is the temperature. So what they're saying here is, remember when pressure, so the other factor that affects equilibrium is pressure. So an increase in pressure naturally increases temperature. But for our purposes, we're going to have temperature remain constant. We don't want two factors changing at the same time. That makes things a little bit complicated. So for now, don't worry about two factors changing at once. We will only deal with temperature changing or pressure changing. So even if pressure is increasing, we will accept that temperature is constant. Another example, okay, I've already actually explained this example with regards to temperature. This is the nitrogen and hydrogen example that I looked at. That's on the previous slide as well, earlier slide. Another factor affecting equilibrium is pressure, and that only has an effect on gas, because remember, when you apply pressure on liquids and solids, it's not going to change them. However, on gases it can. Gases can be compressed. So what we need to look at here is how much of each gas there is on the reactant side and on the product side. How do we determine that? We look at the mole ratio. This is 1, that invisible 1 there, that's 3. So in total the reactants is 1 plus 3, which is 4. And the product is only 2. Something, I just want to interrupt myself here quickly. When we deal with the Le Chatelier's principle, we always want to look at what is the disturbance. Because if we know what the disturbance is, Le Chatelier's principle tells us that the principle needs to be offset. It needs to be counted. Alright, so just a silly analogy. You've gone on holiday and your holiday got extended to lockdown and it's gotten longer. And as it's gotten longer, we've given you more work. Right? So you've received more work from us. So the concentration, the amount of work that we've given you has had an effect on the equilibrium at home. You're no longer lying on the couch the whole time. Okay, so, but now that is the disturbance that's taken place. You've been given more work by us. Alright? Now what do you do with all that work? You need to actually work on it and complete it. So the reactant is the work that we gave you. Right? The product is the work that you produce. So as the disturbance was increased, you had to do something about that disturbance. And to offset it, or to counter this disturbance of the work that you were given, you actually had to go and do work and produce work. And the more work you did, that meant that a new equilibrium was reached. Okay, because you've counted the amount and the volume of work that you've been given. It's just a silly example, right? But hopefully it gives you some understanding of what we're dealing with here. There's always a disturbance, and the disturbance needs to be countered. That's how Le Chatelier's principle works. So now, if we increase the pressure, the reaction will move in the direction that will decrease pressure. Increasing pressure means we need to now decrease the pressure. So how do you do that? Well, if we look at this example here, you've got let's just call it 4 units of gas here, and you've got 2 here. So it's going to move to the direction that produces less. Alright, so if you increase the pressure, it's going to move to the right. It's going to favor the forward reaction because there's less being produced here. I hope that makes sense. There are total of 4 mole here, and there are only 2 here. The same is true if we decrease the pressure. Decreasing the pressure, or you're decreasing the pressure, means you now need to counter that by increasing the pressure. So that means it's going to favor the reverse reaction to counter the disturbance that you experienced there. I hope that makes sense, gents. So we've now discussed the temperature factor, the pressure factor, and we need to still look at the concentration factor. We'll have a look at that just now. So you need to be able to explain an increase in pressure in terms of Le Chatelier. So when the pressure of a system at equilibrium is, let's say, increased, not changed, increased, the system will react to reinstate equilibrium according to Le Chatelier by favoring the reaction which decreases the volume, decreases the pressure. So in this case, the forward reaction will be favored. When the temperature of a reaction at equilibrium is increased, the system will reinstate the equilibrium by favoring the reaction which is endothermic. So in this case, it's the reverse reaction, like I discussed earlier. Okay. Now, this is just an example out of your textbook. Remember, everything we're discussing here is pretty much copy and paste out of your textbook from page 175 to 176. So that's where the theory is, and page 177 is where the exercises start. And this is the first question on the exercises. Just to add to this they show in the textbook, its color is brown, and the color of this substance is colorless. It's clear. Again, we need to look at information that's given to us. These are both gases. There are 2 mole of this. There's 1 here. And this tells us that delta H is negative, which means it's exothermic. It's an exothermic reaction. And it's homogeneous as well. So this flask, or closed system, contains only NO2, nitrogen dioxide. But the nitrogen dioxide reacts to form dinitrogen tetroxide. So you will start off with a brown substance in this flask, and then after a while the dinitrogen tetroxide will form, and that means the amount of nitrogen dioxide will decrease. Obviously it would have to, because the reactant is forming a product. So initially the rate of the forward reaction is high, but it slows down as more of this product is formed. And as more of this product is formed, the rate of the reverse reaction will start increasing as well, up until a point where the rate of the forward and the reverse reactions are the same. Okay. So N2O4 concentration will increase as the reaction proceeds. What will also happen is it will see that this brown color will become more and more colorless, but it won't be completely gone. because at equilibrium there will still be some nitrogen dioxide being produced. So there will be a lighter brown in the flask, not dark brown. The forward reaction will decrease in rate as more NO2 is used up to form N2O4. And obviously it will increase the reverse reaction. This is referring to the reverse reaction will increase. The rate of it will increase as more N2O4 is produced. So yeah, this is just an example of one of the questions in your textbook. And here are a whole lot of other examples from your textbook as well that I don't want to discuss now because you need to go and do them yourself. Just something that's very important that you need to be aware of. The concentration of a pure liquid, such as water, or a solid, remains constant always. You can't change the concentration of water. You think about it. If you got a glass of water and you add more water to the water, it's not going to change its concentration. And the same goes for a solid. Only the concentration of a solution, so an aqueous solution, can be changed, like sodium chloride. Okay. So now we haven't discussed the other factor, the last factor, concentration. So that is a disturbance that can also take place, can disturb the equilibrium. Looking at this one again, nitrogen, hydrogen forming ammonia. If we increase the amount of hydrogen, the reaction must produce more ammonia until the excess of hydrogen is used up, or the amount of nitrogen runs out. So what they're saying here is the disturbance is an increase in the hydrogen concentration. If we increase that, that is the disturbance. We need to counter that disturbance, and the only way you're going to counter it is use up more of the hydrogen gas. By using up more of the hydrogen gas, it will automatically also use more of the nitrogen gas, and it will form more ammonia. So the forward reaction will be favored if you increase the concentration here. If you had to increase the concentration of ammonia, it will favor the reverse reaction to counter the disturbance that's taken place there. I hope that makes sense now. In this reaction over here, we have a solid and a gas as a reactant. Increasing the amount of sulfur is not going to have any effect on the equilibrium. Why? Because sulfur is solid here. You're not going to change the equilibrium by adding more of the solid because its concentration doesn't change. Here's just an example of an equation that has an aqueous solution. It's got a solid, aqueous, and liquid. Again, changing the concentration of aluminium hydroxide, which is a solid, or of water, which is a liquid, is not going to change or have an effect on the equilibrium. We can only affect the equilibrium by having increasing or decreasing the concentration of hydrogen chloride or aluminium chloride. Obviously, other changes can take place to the equilibrium by changing the temperature. There are no gases here, so increase in pressure or decrease in pressure won't have any effect. Okay. So, gentlemen, I hope that what I've shared so far has helped. Like I said, I'm new at this, and I'm still learning, but I really hope this has helped. This is what you need to go and do now. Don't worry, there is no 14.3 as far as I could tell from in the textbook, so don't stress about that. But go ahead and try these, and if you have questions, please comment on this video or send me a message, and I will gladly assist where I can. Alright, have a good day and lock down further, gents.